You know, when we think about physical fitness, I feel like the images that come to mind are almost entirely mechanical.
Oh, absolutely. Like pulleys and levers.
Right. It's all physics. You lift a heavy weight, you generate tension, muscle fibers tear, they rebuild, and you get stronger. It just feels like gears turning in an engine.
Yeah, but that's really just the surface level.
Exactly. Because when you bypass all that physics and dive into the actual physiology of it, you realize your body isn't some mechanical engine at all. It is this wildly complex, hyper chatty chemical communication network.
It's an entire hidden language, really, happening right under the surface. We always focus on the muscle pulling the bone, but we completely ignore the millions of chemical text messages flying around the bloodstream that actually make that movement possible.
Which is exactly what we are getting into today. Welcome to this deep dive. We are taking a dense stack of physiological texts, and we're specifically zeroing in on the endocrine system.
And specifically how physical training completely rewires it.
Yeah. We are bypassing all those high school biology basics today to look at the absolute cutting edge of how our bodies communicate chemically. So we're talking about how your muscles are secretly acting as glands, how exercise essentially installs a back door into your cells, and honestly, the bizarre fact that the fitter you get, the quieter your body's chemical signaling actually becomes.
I love that last point. That idea about endocrine efficiency in athletes completely upends how most people assume human performance works. But, I mean, to really grasp how exercise alters our chemical signaling, we need to clarify how these messages are packaged and delivered in the first place.
Okay, let's unpack this, because the nervous system usually gets all the glory, right?
It's
Just
really
because it's fast.
Very fast, instantaneous, basically.
Right, it's a direct, wired fiber optic cable. The signal travels instantly from point A to point B, and the second you pull the plug, it just stops. But the endocrine system, on the other hand, is completely wireless.
Yeah, that's a great way to put it.
If we were using a tech analogy, it's like a massive systemic Wi-Fi network.
Mhm.
A ductless gland, and we should note, endocrine means ductless. It secretes right into the blood, unlike an exocrine gland, like a sweat gland that uses a duct. So this ductless gland, somewhere in the body, hits send. It releases a hormone.
Which literally means impetus in Greek, by the way.
Impetus, right?
Oh, boy.
So it releases this hormone into the bloodstream. And that message washes over every single organ in the body. But only the specific devices with the right password, meaning the correct cellular receptors, can actually read the data and react to it.
What's fascinating here is the sheer precision and, frankly, the absurdity of the scale involved in that receptor mechanism. Because hormones, they do not operate like a flood. They operate in these minute, almost incomprehensible quantities.
Like how small are we talking?
We are looking at concentrations in the nanomolar or even picomolar ranges.
A picomole.
Yeah, a picomole is 1/1,000,000th of a mole.
Oh, wow. That's insane.
It really is. It's the equivalent of dropping a single grain of sugar into an Olympic-sized swimming pool and expecting the water to suddenly taste sweet.
That's entirely unintuitive.
Right. Yet when that single hormone molecule binds to its specific receptor on a cell membrane, it initiates a massive, cascading biochemical avalanche.
See, that's where my intuition completely breaks down. If the hormone is just a single tiny molecule, and as the research points out, most of these peptide and amine hormones don't even physically enter the cell, they just dock on the outside surface.
Yeah.
So how on earth does it force the cell to change its internal behavior?
Well, it does it by using a proxy. Because the hormone can't pass through the lipid membrane, it binds to the surface receptor, which then alters its shape.
Okay.
And that shapeshift activates an enzyme inside the cell wall, usually adenylate cyclase, which then generates what we call a second messenger.
Second messenger, got it.
Yeah, the most common one is cyclic AMP. That second messenger is the real trigger. It activates a whole series of protein kinases, which then phosphorylate other enzymes. So think of it as a literal biochemical domino effect.
Right, so one molecule on the outside triggers the inside.
Exactly. One single hormone molecule docks on the outside, and within milliseconds, the cyclic AMP inside is knocking over thousands of dominoes, furiously altering protein synthesis, changing enzyme activity, opening up membrane channels, all of it.
So it's basically a massive amplification system. One tiny knock on the front door echoes through the entire building. And unlike a nervous system zap, this chemical echo actually lingers.
Exactly. The effect is dictated by the hormone's clearance rate, or its half-life. Some small peptides are swept out of the blood in a few minutes, but steroid hormones, which use transport proteins, by the way, they can circulate for hours or even days before the liver and kidneys finally clear them out.
Okay, so if the hormones are these hyperpotent Wi-Fi messages floating through the blood, The natural question is, well, who is the network administrator? What triggers a gland to broadcast a message in the first place?
The body essentially uses three primary triggers for this. There's humoral stimulation, which is a direct response to changing blood levels of ions or nutrients.
Like blood sugar?
Yeah, exactly. The pancreas tasting high glucose and releasing insulin is a humoral response. Then there's neural stimulation, where nerve fibers directly shock a gland into action, like when the sympathetic nervous system triggers the adrenal medulla to just dump epinephrine right before a heavy deadlift.
Oh, I know that feeling.
We all do. And finally, there's hormonal stimulation, where one hormone's entire job is just to travel to another gland and tell it to release a different hormone.
Here's where it gets really interesting, because when we look at that third trigger, hormones bossing around other hormones, we find that for centuries, the medical field completely misunderstood the chain of command.
Oh, totally. They had it completely backwards.
Yeah. The texts note that Galen, the famous early Greek physician from the 2nd century AD, he actually identified the pituitary gland at the base of the brain. But he assumed its primary function was to act as a funnel.
A funnel for what, though? This is the best part.
Right, he thought it was draining waste phlegm from the brain down into the nasal cavity.
It's just a hilariously gross misinterpretation of neuroanatomy.
It really is.
But, I mean, given the tools of the 2nd century, you can somewhat see how he arrived at the idea of a structural funnel.
Sure, I'll give him a pass on the phlegm thing. But even after we realized it wasn't a phlegm drain, for the next 19 centuries, medical textbooks proudly labeled the pituitary as the master gland of the body. They thought it was the absolute top of the pyramid.
They really did.
But the modern physiological consensus shows the pituitary is basically just a middle manager taking all the credit. The true CEO operating from the shadows, dictating everything the pituitary does, is the hypothalamus.
Yes. The hypothalamus is the ultimate bridge between the nervous system and the endocrine system. It receives all the raw neural data about the body's state. So temperature, stress, light exposure, all of that.
Right.
And it translates that into chemical orders. It secretes releasing and inhibiting hormones that travel down this highly specialized, very localized blood vessel network called the hypophyseal portal system.
Which goes directly to the pituitary.
Directly to the anterior pituitary. It literally holds the middle manager on a short leash. If we look at human growth hormone, or GH, you can see this dynamic perfectly.
Right, because growth hormone is notoriously misunderstood in fitness circles. People just think of it as simple muscle-building juice. But the pathway is much more complex. The hypothalamus has to initiate the sequence, right?
Precisely. The hypothalamus evaluates the body's stress or energy demands and releases growth hormone-releasing hormone. That local message tells the anterior pituitary to finally secrete GH into the general circulation.
And once it's out there.
Once GH is out there, its effects are sweeping. It doesn't just make things grow. It actively shifts the body's entire fuel economy. It promotes cellular proliferation and protein synthesis by drastically increasing amino acid transport across cell membranes.
Okay, so it builds tissue.
It does, but simultaneously, it tells the cells to stop utilizing carbohydrates and instead start mobilizing fatty acids for energy, so it preserves blood glucose while building tissue. But again, the pituitary can't initiate that massive metabolic shift without the explicit, localized chemical permission of the hypothalamus.
So we have the brain, acting as the CEO, sending localized memos to the pituitary, which then blasts the chemical Wi-Fi out to the rest of the body.
Yeah.
That top-down model was the established, unquestioned scientific paradigm for decades. But the sources highlight a massive paradigm shift that completely shattered that model in 2003. Researchers discovered a completely unexpected role player in the endocrine system.
This is one of my favorite discoveries. They realized that skeletal muscle tissue is not just a dumb mechanical target. Skeletal muscle is actually an active endocrine organ.
That is just wild to me. We've always viewed muscles simply as the receivers of the signal, Insulin acts on muscle. Growth hormone acts on muscle. The idea that a bicep or a quad is actively producing and broadcasting its own hormones flips the entire script.
It radically changes how we view locomotion. The discovery in 2003 identified that when muscle fibers physically contract, The mechanical and metabolic stress causes them to produce and secrete small signaling proteins called cytokines.
Okay.
And because they originate in the muscle, we call them myokines.
And the primary one the research zeroes in on is interleukin-6, or IL-6, right?
Yes, IL-6. When you are engaged in sustained physical activity, your contracting muscles produce IL-6 and dump it into your circulatory system. This myokine acts as a direct line of communication between your moving body and your adipose tissue.
Your body fat.
Exactly, your body fat. When IL-6 binds to the receptors on fat cells, it stimulates lipolysis, which is the breakdown of stored triglycerides into free fatty acids.
So the muscle isn't just passively waiting for the brain to notice the energy deficit. The working muscle is literally picking up its own chemical phone, calling the fat stores directly and saying, hey, we're doing heavy squats down here, we are chewing through ATP, break open the vaults and send us fuel immediately.
If we connect this to the bigger picture, that signaling mechanism completely reframes the purpose of exercise. You aren't merely burning calories through mechanical friction. You are intentionally forcing your muscle tissue to secrete specific hormonal profiles that orchestrate your systemic cellular health.
Wow.
And the inverse is perhaps even more critical. Like, what happens to the body when that chemical signal goes totally silent?
Which is exactly where the spaceflight data comes in. The text brings up the Crucian studies on astronauts, and it is a brilliant but kind of terrifying illustration of this.
It really is.
So they tracked crew members on the International Space Station, right, analyzing their blood plasma. When you are in a microgravity environment, your muscles aren't constantly firing to fight gravity. There is zero resistance. So without that constant low-level muscle contraction, the IL-6 pulse just flatlines.
And the physiological fallout is immediate. The astronauts didn't just experience muscle atrophy, they exhibited persistent immune dysregulation.
Because then the muscles stop talking.
Exactly. Without the regular chemical chatter from the muscles, their systemic cytokine levels became completely skewed. The blood markers showed patterns of persistent inflammation combined with this bizarre suppression of normal immune function. The body's defense network essentially lost its mind because the muscles stopped sending their daily status reports.
So physical activity is quite literally a biological prerequisite for normal chemical signaling. If you sit in an ergonomic office chair for 14 hours a day, it's not that different from microgravity. Your muscles go quiet, the Wi-Fi signal drops, and your systemic networks start failing. And I think the most glaring, catastrophic example of that metabolic failure in the modern world is peripheral insulin resistance.
Oh, absolutely. The current epidemic of type 2 diabetes is the ultimate manifestation of a broken chemical communication network.
Since we're looking past the basic definitions today, let's focus on the actual mechanics of that failure. We know the pancreas manages the energy seesaw, so it secretes glucagon to release stored sugar when we need it, and insulin to usher sugar out of the blood and into the tissues when we have a surplus.
Right, that's the healthy loop.
Yeah, in a healthy system, it's a really tight loop. But in type 2 diabetes, the pancreas is usually still working. It's pumping out insulin. The issue is actually at the cellular level.
Yes. The peripheral tissues, primarily the liver, fat, and skeletal muscle, they become severely insulin resistant. The hormone is in the blood, but the receptor sites on the cells are effectively deaf to the signal. And we should note, this is distinct from type 1 diabetes, which is an autoimmune destruction of the beta cells where there's an absolute lack of insulin.
Right. Type 1 is a lack of production. Type 2 is a lack of reception. And the numbers on type 2 are staggering. The sources mentioned that in 2012, 29.1 million Americans had diabetes, making the U.S. the third highest globally.
It's an absolute epidemic, heavily linked to the modern Western lifestyle of high fat and low physical activity.
So what does this all mean? How does the reception actually break? I think a bouncer analogy works really well here.
Oh, let's hear it.
So imagine the cell is an exclusive nightclub. And glucose is a bunch of people trying to get inside. Insulin is the bouncer trying to let the glucose into the club. Normally, the bouncer checks the list, opens the velvet rope, and glucose goes in. But in type 2 diabetes, driven by a hypercaloric diet and chronic inactivity, there's just too many people.
The bloodstream is flooded 24/7.
Right. The music inside the club is blasting. It's totally packed. So the bouncer, insulin, is yelling, trying to push more people in, but the cell is just like, nope, we're at capacity. The music is too loud, the club ignores the bouncer entirely, and the door stays shut.
That is a highly accurate way to visualize peripheral downregulation. The cell protects itself from energy toxicity by ignoring the signal. But the pancreas doesn't know the club is ignoring the bouncer. It just senses dangerously high blood sugar out on the street.
So it panics.
Exactly. It panics and produces even more insulin, hiring more bouncers to try and shout over the noise, leading to hyperinsulinemia. You end up with a bloodstream chronically toxic with both elevated glucose and elevated insulin, which damages the vascular endothelium.
And the clinical tracking of this damage isn't just a basic fasting glucose snapshot, right?
hmm
The texts highlight the hemoglobin A1C test, which is fascinating mechanically.
It really is a clever diagnostic. The HbA1c test measures glycosylated hemoglobin. When glucose concentrations in the blood remain chronically high, the glucose molecules physically bind, or glycate, onto the hemoglobin proteins inside your red blood cells.
So it's literally sticking to the blood cells.
Yes, and it's not a temporary physiological state. It is a permanent structural alteration of that specific cell. Because a red blood cell has a lifespan of about 120 days, measuring the percentage of glycation provides a highly accurate historical average of your blood glucose levels over the preceding 2 to 3 months. It catches the chronic dysfunction that a single fasting test might just completely miss.
That makes total sense. So if a sedentary lifestyle and a constant influx of processed carbohydrates cause the cell to lock the doors and broke the insulin system, how do we fix it? Because we can't just take a pill to install a new bouncer. But the source material makes it incredibly clear that exercise is a profound, active, non-pharmacologic therapy.
It is the single best intervention.
But how exactly does mechanical muscle contraction bypass a chemically broken insulin receptor?
It essentially installs a backdoor. Earlier, we established the absolute necessity of glucose for active muscle tissue. But during exercise, the muscle cannot afford to wait around for the broken insulin pathway to slowly grant access to fuel. So the body evolved an override.
A completely separate pathway.
Exactly. Inside the muscle cell, there are specific transport proteins called GLUT4. When the muscle fiber experiences mechanical tension and the chemical stress of calcium ion release during contraction, those GLUT4 vesicles physically migrate from deep inside the cell to the outer membrane.
They literally rise to the surface.
They do. They embed into the membrane and open wide, allowing massive amounts of glucose to pour out of the bloodstream and into the working muscle entirely independent of insulin. The physical act of contracting a muscle forcibly sweeps glucose out of the blood, completely bypassing the ignored bouncer at the front door.
That is an incredible piece of biological engineering. You don't need to fix the front door if you can just blow a hole in the side of the building while you're working out.
Well put. And the therapeutic benefit extends far beyond the duration of the workout itself. Regular physical training actually upregulates the cell's overall sensitivity to insulin in the hours and days following the exercise bout. The cellular environment changes. Over time, you need significantly less insulin to manage the exact same carbohydrate load.
Which transitions perfectly to perhaps the most counterintuitive, mind-bending finding in this entire deep dive. We've talked about the immediate effects of a workout, but let's look at the long-term adaptations.
Let's do it.
Because I would naturally assume that a highly trained, elite endurance athlete is just a biological powerhouse. I picture a souped-up, roaring sports car engine. I'd assume that because they can run like a sub-3-hour marathon, their body must be pumping out massive, overwhelming volumes of adrenaline, cortisol, and growth hormone to sustain that extreme output.
This raises an important question about how we fundamentally define physiological optimization. Your intuition aligns with how we view mechanical power. Bigger engine, more fuel, louder roar. But in the endocrine system, true fitness looks entirely different. Long-term endurance training actually decreases the magnitude of the hormonal response to a standardized physical stressor.
Wait, it decreases it. So the fitter you are, the less hormone you produce during the exact same run.
Yes. If you take an untrained, sedentary individual and force them to jog at a 6-minute mile pace, their neuroendocrine system perceives it as a 5-alarm biological crisis. Their blood levels of epinephrine, norepinephrine, cortisol, and growth hormone will spike violently. It is a massive, frantic chemical dump to try and keep the body moving.
Just sheer panic mode.
Total panic. But if you train their individual for a year, their cardiovascular system adapts? Sure. But more importantly, their endocrine receptor sites become hyper-optimized.
They become more sensitive to the Wi-Fi signal.
Precisely. The target tissues are so effectively primed that it requires only a fraction of the hormonal signal to achieve the exact same metabolic output. If you have them run that same 6-minute mile a year later, their chemical response is drastically blunted. A highly trained athlete's endocrine system isn't a roaring, wasteful V8 engine. It is a whisper-quiet, frictionless magnetic motor. They execute massive amounts of physiological work with remarkably quiet chemical signaling.
That reframes everything. Being fit isn't about your glands shouting louder. It's about your cells finally listening better. You become a more efficient conductor of the signals.
And there is one additional highly specific chemical adaptation to exercise that we must highlight, one that directly rewards this physical effort. In the 1970s, researchers made a massive breakthrough regarding pain perception in exercise.
Ah, the discovery of the exercise high.
Correct. Researchers isolated endogenous opioid peptides, meaning specialized opioid structures synthesized naturally inside our own central nervous system. They named them endorphins, which is literally a portmanteau for endogenous morphine.
Endogenous morphine. Wow.
Yeah, these neuropeptides bind to the exact same opiate receptors in the brain as external narcotics.
So a runner's high isn't just a psychological mood boost or some metaphor. It is a highly specific, measurable chemical event.
It is a literal pharmacological intervention executed by your own brain. During moderate to intense, sustained physical exertion, the body secretes these beta endorphins. They effectively block pain signals, improve appetite regulation, massively reduce anxiety, and induce a transient state of euphoria.
That's amazing.
From an evolutionary perspective, it is a built-in survival mechanism designed to mask the acute tissue damage and discomfort of pushing your physical limits, basically rewarding you for locomotion.
It is just wild to step back and look at the whole picture we've painted today. We started this deep dive thinking of hormones as this abstract, confusing textbook topic, just a bunch of unpronounceable molecules.
Right.
But when you strip away the jargon, it is the profound story of how our physical flesh talks to itself. We moved from early Greek physicians literally thinking the brain was an anatomical phlegm funnel to understanding the hypothalamus as a master CEO dictating a hyper-precise chemical intranet.
And we completely shifted our perspective on skeletal muscle, realizing that every time we move, our muscles are acting as rogue endocrine glands, shooting text messages to our body fat and keeping our immune system from attacking itself.
Right. And seeing the physical mechanics of insulin resistance, how a hypercaloric lifestyle forces the cells to ignore the bouncer and lock their doors. But the sheer brutal act of mechanical muscle contraction physically opens a back door via GLUT4 to clear the blood of glucose, fixing the machinery from the inside out. Ultimately, achieving physical fitness doesn't just make your muscles bigger. It makes your entire chemical communication network quieter, sharper, and vastly more efficient.
It is an incredibly elegant, self-regulating system. But there is one final, almost hidden detail buried in the margins of the physiological texts that I think leaves us with a necessary, slightly unsettling question.
Oh, what's that?
The sources note that hormone secretion does not occur at a steady, flat rate. The vast majority of endocrine release happens in pulsatile 24-hour daily cycles, known as diurnal variations.
So the entire Wi-Fi network operates on a strict biological clock.
Exactly. Our entire chemical communication system, from the cortisol surge that physically wakes us up in the morning to the massive pulses of growth hormone that repair our cellular damage in the deep stages of sleep at night, it is all inextricably linked to the rotation of the planet. It is synced to a 24-hour rhythm of light and dark.
Which means?
It forces us to ask, what actually happens to this hyper-precise, finely tuned chemical machinery when our modern habits relentlessly collide with it? When we are staring at blue light screens at 2 a.m., working erratic shift schedules, and chronically snacking around the clock, are we fundamentally scrambling the very chemical language our cells evolved to speak?
That is a heavy, necessary thought to chew on. If you want your body's internal Wi-Fi signal to remain strong, clear, and efficient, maybe the first step isn't just hitting the gym. Maybe it starts with respecting the clock. Thank you for joining us on this deep dive into the incredible hidden machinery of your own body. Until next time, keep exploring.